Hello students. Yesterday I had uploaded lecture on the series loaded resonant converter. Today we will go on to the next topics of the series loaded resonant converter. But because I think I did not do justice last night, so I'm going to recap the first case, that is the discontinuous conduction case. So what we see on the screen right now is a series loaded resonant converter, wherein, as you can see, there is a resonant circuit comprising of LR and CR. Inductor current, the inductor LR current is IL with the assumed positive direction as shown, and the capacitor voltage VC with the assumed polarity as shown. To the left of the resonant circuit, you have a DC supply VD, which with the help of the two switches T plus and T minus in conjunction with the antiparallel diodes can apply either a positive voltage on the input side or a negative voltage on the input side. If T plus is on or if D plus is conducting, then the voltage applied to the input of the resonant circuit will be plus VD by 2. Whereas if T minus is on or if D minus is conducting, then the voltage applied to the input side will be minus VD by 2. Similarly, on the output side of the resonant circuit, you see there is a full bridge rectifier. So if the inductor current is positive, it will flow through these two diodes, so that B dash is connected to plus V0 and B is connected to minus V0, or the voltage B dash D will be equal to plus V0. Whereas if the inductor current is negative, it will flow through this path like this. These two diodes will be conducting, these two diodes, so that the point B dash is connected to negative of V0, whereas B is connected to positive of V0, so that B dash D will be equal to minus V0. So here in figure B, we have the equivalent circuit of the series loaded resonant converter, wherein there is the resonant circuit. On the input side, you have either plus VD by 2 or minus VD by 2, depending on which device is on the input side are conducting, T plus T plus or T minus or T minus. And on the output side of the resonant circuit, you have a voltage of plus V0 or minus V0, depending on whether the inductor current is positive or negative. The reason why it is called a series loaded resonant converter is that the load effectively appears in series with the resonant circuit. So, these are the circuit waveforms in the discontinuous induction mode when the switching frequency is less than half of the resonant frequency. So I've sent to this PDF today, wherein in the first circuit, we have the basic resonant circuit. DC voltage VD, LR and CR that we had solved previously when we had studied the basic resonant circuit concepts. And we had derived the equation for the inductor current. Inductor current IL of T was equal to IL0 cos omega 0 T plus VD minus VC0 by Z0 sin omega 0 T. And the capacitor voltage was VD minus VC0 cos omega 0 T plus Z0 IL0 sin omega 0 T. Where omega 0 was the resonant frequency given by 1 upon under root of LR CR. And Z0 was the characteristic impedance given by under root of LR by CR. So yesterday I had derived the equations. Today I'll show that we don't need to derive again. We can simply obtain the equations that we had got on this circuit. So here in the first case, at omega 0 T0, we are turning on T plus. So because T plus is turned on, the voltage VAB, the input voltage to the resonant circuit, is plus VD by 2. And because the inductor current is positive, the voltage V dash B is equal to plus V0. So this is that circuit. The initial conditions here are IL0 is equal to 0. The initial capacitor voltage is minus 2V0, which we had assumed. And if we solve for the whole cycle, we see that at the end of the cycle, the capacitor voltage will be equal to minus 2V0. That is why it is the initial voltage here. Now in this case, this VD here becomes equal to VD by 2 minus V0. So if we substitute these in these equations, IL of T, IL0 is 0, so this term disappears. VD we substitute VD by 2 minus V0, and VC0 we substitute minus 2V0. So we get IL of T is equal to VD by 2 plus V0 upon Z0 into sin omega 0 T. And the capacitor voltage, again we substitute VD is equal to VD by 2 minus V0. and Vc0 is equal to minus 2V0, you'll get Vc of t is equal to Vd by 2 minus V0 minus Vd by 2 plus V0 cos omega 0 t. So in the first instance, when t plus is on, this is the inductor current and this is the capacitor voltage. At the end of the half cycle, inductor current reduces to 0 and the capacitor voltage rises to Vd. At this instant, the current tends to reverse because t plus t minus is yet to turn on. The path available for the negative current to flow is through d plus. So here d plus turns on, and again with d plus on, the input voltage is still Vd by 2, and because the current is now negative, this voltage becomes minus V0. This voltage becomes minus V0. So if we again see the initial conditions, then the initial inductor current is 0, the initial capacitor voltage is Vd. This voltage Vd now becomes equal to Vd by 2 plus V0. If you substitute this, you get IL of t is equal to minus Vd by 2 plus V0 upon Z0 sin omega 0 t, and the capacitor voltage is Vd by 2 plus V0 plus Vd by 2 minus V0 cos omega 0 t. Note that V0 is less than or equal to Vd by 2, which means that this current is actually negative, or it is a negative sinusoid. So when d plus is on, you have a negative sinusoid here, and at the end of another half cycle, the inductor current becomes 0, the capacitor voltage reduces to vice V0. At this instant, we are not turning on T minus, there is no path for the current to flow, so the capacitor maintains its voltage at VC. Then T minus turns on, and this positive half cycle repeats in the negative direction. So this is one half cycle of the resonant frequency, one cycle of the resonant frequency. This is another cycle of the resonant frequency, and this is one cycle of the switching frequency. So here the switching frequency is less than half of the resonant frequency. So when we keep in this SLR converter, when we keep the switching frequency less than half of the resonant frequency, we obtain discontinuous conduction. The disadvantage of this circuit is the high value of inductor current, which increases the losses in the circuit. The next mode that we have to study is the continuous induction mode, in which we are keeping the switching frequency greater than half of the resonant frequency, but less than the resonant frequency. So what is happening here is, initially we are turning on T plus at omega 0 T0 at some finite current and voltage. The switch here is turning on at finite current and voltage. In the previous case, the diodes, the switches were turning off naturally at 0 current and at 0 voltage. They were turning on at 0 current but not at 0 voltage. Diodes were turning on and turning off at 0 current. Here in this case, what is happening? We are turning on a T plus at some finite value of current and finite value of voltage. There are going to be turn on switching losses. So when we turn on T plus, the inductor current is positive. Again, the equivalent circuit is same. We can solve again as before, or we can use the previous circuit, basic circuit, and substitute the values. So here the inductor current is flowing. Earlier D minus was conducting, there was some finite value of current. We turned on T plus, inductor current is flowing, and it becomes 0 at omega 0 T1. Now the current wants to reverse, and because T minus is not yet turned on, the inductor current will now flow through D plus. At this instant, before the diode current can reduce to 0, we are turning on T minus again at some finite value of current. Again, the negative current reduces to 0 at this point. Now it has no option but to flow through D minus, and so here one cycle is completed. Of inductor current and capacitor voltage is completed. So what is happening here is, the switches are turning on at finite current and finite voltage, but they are turning off at 0 current and 0 voltage. So there are no turn off losses, there will be only turn on losses. As compared to the previous case, the maximum value of inductor current will be less here, and that is why the losses in the circuit will be less. The third case is continuous conduction with the switching frequency greater than the resonant frequency. What is happening here is we are turning on T plus at zero current. Okay? The switches here, unlike the previous case where the switches were turning on, they were turn on losses but no turn off losses. Here there will be no turn on losses, there will be only turn off losses. So T plus is turned on at omega 0 T0, the current starts increasing, and before it can reduce to zero, T plus is turned off. Okay? It is forced to turn off. That is why you need controllable switches here. SCRs will not work here. In the previous two cases, we could have used SCRs because the switches were turning off at zero current. Here the switches are not turning off at zero current, so if we use SCR, we'll need a forced commutation circuit. So instead of that, it is better to go for controllable switches. Before the current can reduce to zero, at some finite value of current, we are turning off T plus. Because T plus is now turned off, and the inductor current is still positive, it has no option but to flow through D minus. It has to flow through D minus. So the current will continue to flow through D minus, and because a large negative voltage is applied across the LC tank, this current will be forced to zero faster. Okay. As you can see, if this had followed, it would have reduced to zero after some time, but because of the large negative voltage applied across the LC tank, and D minus is conducting. I think I've shown you before the value of V dash P, and D minus is on. Because of the large negative current, the diode D minus, the current is flowing through D minus, it will be close to zero earlier. As soon as the current reduces to zero, we turn on T minus. As soon as the current reduces to zero, we turn on T minus. So T minus is turning on at zero current as well as at zero voltage, because at the instant when T minus was turned on, D minus was conducting earlier. The voltage across T minus was zero. So T minus is turning on at zero current and zero voltage. T minus turns on at zero current and zero voltage, and again here T minus is forced to turn off at some finite value of current and voltage, and then the current will go through T plus. So the advantage of this circuit as compared to the discontinuous conduction case is that the peak inductor current is less, so that the losses are reduced. So this was the series loaded resonant converter. In the next video, we will see what is the parallel loaded resonant converter. That's all for now.